Um, um, Thanks. My name is Ramon Tortosa. I work for Analog Devices here in Valencia. It's a beautiful city. Just realized from previous talks that I have too many slides. Okay, so I'll try to go fast through it. Okay, and stop on the important points. So I'll start with a useless definition. Okay, what is multi-touch? And it's useless because you will know what it is. You will experience every day on your mobile phones. So, but I thought it was a good way to start with the easy part. So multi-touch is just you're able to detect on a screen multiple simultaneous touches. Okay, so you can track fingers around, do different things with these movements. Okay, like gestures. Okay. So as I say, able to simultaneously register distinct positions, and then do many things with that, as you probably know on your mobile phones. Now, to do that, we need to implement some kind of circuit to detect touches. And nowadays, I think all the screens are done with capacitive sensing. Okay. And that is, we detect the changes in capacitance on on the screen. That is a conductor that is built with ITO, which is a transparent conductor of about 100 ohms per square. And so we have to detect the position, and we measure capacitance of sensors on the screen, and when you put your finger on one of those that changes capacitance, we measure that change in capacitance. Okay. There are different flavors of these sensors, and one of the differences is what capacitance you measure. On this case, for this work, it was the capacitance to ground, what we call the self-capacitance. So we excite the sensor, we measure capacitance, and we measure it continuously and detect where it changes when you put your finger down on the sensor. Okay. So because it's a ground sensing, what we measure is a change, as I'm trying to outline here, is a change in the delta. Okay. A change in the cap. So whenever we don't touch, we have a certain bulk capacitance. Then we touch down, we have an extra capacitance that we try to measure. And there are different problems here. One of them is, let's say, we have, this LCD noise. So the LCD, you have to think about, and as you know, the LCD is at the bottom of this sensor. The sensor on top of the LCD is changing electrically. That causes noise. On your measurements, noise you have to deal with. Okay. So we had a customer that actually builds these ITO screens and wanted us to design an ASIC for them. And what they propose is a single layer ITO. So in most phones that you have, it's a 2-layer ITO. And you measure capacitance between these 2 layers. And this customer wanted to build a single layer ATO. So we measure capacitance to ground, whatever that ground was, and when you put your finger down, that changes, measure the change. Okay. So having a single ATO have certain advantages, like lower cost, the reduced stack height. That is, when you build your module, obviously you have more layers. The height is higher, so it's bulkier. And so they came to us because we have some experience with cap touch ASICs. Okay. So there's some details in the panel construction. Is a pattern ITO, as you can see here. Each of these squares is a single sensor that needs to be routed to the ASIC that should be sitting somewhere here. So there's individual routing that goes in between these sensors, comes on the side of the panel and goes down to the ASIC, okay? As I said, as if the user moves his finger over these sensors, we sense the change in capacitance, okay? Chip on glass technology, in this case, is used to actually connect the ASIC onto this panel. So this would be the ASIC we develop, and it's just it's actually integrated with the panel itself. There are 96 of those sensors with it's kind of an offset, both what we call bulk capacitance of 7.5 picofards and a delta of 1 picofarad when we put the finger down. That is one of the advantages of using self-capacitance, is that change is much bigger than when you use mutual capacitance between sensors. And that was one of the advantages of using this single ITO panel. So at the first cut, we actually modeled these as just individual caps, one per sensor. In our, in order to design the system, we needed a model to simulate the panels. So we started with this, completely independent with some routing resistance to each sensor. The ASIC that was developed is just, this is the front end, where you have 96 individual AFEs. It has some nice features. It has an MCU on chip too, then some logic to control the AFEs, and standard input-output, PRs. So one of the important things is that it has an MCU on chip too, a microcontroller. Just a picture, because it's always nice to show pictures in presentations. That's the ASIC, and that's where it sits in this kind of evaluation panel that we use in the lab. So we have these 96 readings from all these sensors, and from there on, we need to somehow calculate where the finger is. We need to position the finger on the screen. And you may have noticed, these sensors are quite big, okay? So, and the resolution on your phones is much finer than that. I mean, you should be able to point your finger almost at the pixel level of your screen, right? So, what you do is actually combine inputs from many sensors and do a kind of a fitting of a curve if you have. Obviously, the sensors that are farther away from your finger have less capacitance, and the one you're closest to has higher capacitance. Then what you do is just look for the peak. That's the finger. Or there may be many algorithms to find your peak, okay? So what we do, in our case, in our evaluation, was just to use a kind of a simple center of masses algorithm. It looked at the sensors and calculated where the center of masses was. So in the first evaluation, what we saw was something like that. It's quite bad, actually. So we saw that even though we calibrated these, so in order to calibrate this, what we did is we had a robotic arm, and we placed one after the other all the sensors. We put accurately the artificial finger on the sensor, measured capacitance and the delta, calibrate that out. But then when we moved to different positions, we saw that there was a problem with the measurement. Okay, as you can see, and it kind of followed a certain zigzag pattern somewhere, because, and we found out later on that it was because of the way the routing was. Okay, as I said before, the routing is placed in between the sensors because it's a single layer, so you can't actually place routing underneath or anything. It has to go in between the sensors. So we obviously needed to look at what was happening. That was we had an error of max error, so that is the max length of any of these arrows is 1.6 millimeters. So we needed to find a way of reducing that. First, find what was going on, and then try to fix this. So we start thinking that maybe it was coupling between the traces, actually the routing that you have, and the sensors, and routing to routing. Because if you had only the sensors, because sensors are symmetric, the coupling between sensors should not affect your accuracy, okay? But because the routing is not symmetric, it might affect how you position your finger, okay? So we built a model of the whole panel and do simulations, and we actually saw that that was the case. So one way of so the problem was that it was actually the routing had some coupling to the other routing and to the sensors. Way of fix that. There are several ways, obviously, to space them out, move them apart. That was not an option anyway, because the restrictions in your panel. Or placing ground tracks between the tracks, and again, that is not possible because of restrictions. So just to let you know what kind of model we had for simulation to reproduce the system. Also, reproduce the error was just take this whole sensor, replace it with just caps between routing and sensors, and just put up a full mesh of caps and resistance. Okay. Now. So what we end up doing was to apply a correction matrix. This matrix, what it does, it looks at capacitance, coupling capacitance between routing, and try to build a correction that we can apply on the run. Okay. So the idea is just simple. It's not rocket science anyway. It's but we have real measurements. What we want to do. So the real measurements are affected by a kind of a matrix of couplings between or parasitic couplings. So if we have that matrix, we can actually invert that matrix and have a better reading out of the real ones. Okay. This is just, and that as I say here, this matrix is dependent on these capacitance I showed you before, the kind of the parasitic capacitance between routings. Okay, show you effects. This is what we showed you before. We build up matrix, and so as you can see, the error here, you might know, it's kind of hard to see here graphically, but it was reduced from 1.65 to 0.99 millimeters on the run. This is running, so you don't see that, when you move your fingers across the panel. Now, you may wonder, this correction matrix, it might be just a beast, something you can't really implement, but it turned out that it's very sparse. So when you invert that matrix, there's a lot of numbers there, but when you look carefully to it, there's certain things we can use to simplify that. One is the kind of in the diagonal is almost 1, and outside this there's a lot of elements that are close to 0. So you can simplify this a bit. Okay. This is the values of that matrix in a graphical form, all of them. When we actually simplify it to 8 bits, they're reduced, obviously, and we keep reducing that. When we go to 6 bits, actually the sign bit is lost. You don't need that anymore. Again, reducing that to 5 bits, 8 bits. This is let's get us a table where we have the effect of that quantization. As we decrease the bits, we increase the error, and we ended up using these 6 bits that gave us this error, and that is about 300 elements in that matrix. That is really, it's not really a big problem. Just dump it into the MCU and use this on the run. Okay. So pretty much the conclusion is just that we were able to produce a matrix that is fully integratable and put in the chip, and it runs. It kind of runs as you move your fingers across. It doesn't affect the refresh, and having an MCU made it possible too. So thank you, and sorry for that rush presentation. Okay, and if you have any questions.